When training AI on biomedical signals like EEG or ECG, you hit a wall: cross-subject generalization. Two patients with the exact same condition can produce wildly different waveforms. Most models just try to blur out these personal differences, treating them as noise. But what if they're not random? What if they follow a predictable mathematical structure? Researchers found that signals from the same condition actually share a consistent oscillatory skeleton. The variation isn't noise, it's spectral drift. Each individual signal gets shifted in amplitude and phase across specific frequency bands. To fix this, the new architecture, BioFormer, operates directly in the frequency domain. Instead of forcing uniformity, it uses a frequency band alignment module. This module leverages cross-attention to compare a signal's band statistics against learned templates, then generates precise modulation factors. These factors independently scale the amplitude and rotate the phase of each band. Crucially, it uses a residual update approach, meaning it only applies the minimal necessary correction, preserving the task-relevant physiological features. To stabilize training across subjects, BioFormer integrates Sample Conditional Layer Normalization, or SCLN. Rather than relying on subject IDs, SCLN adapts features based on each signal's internal statistics. Interestingly, ablation studies show SCLN works best at the extremes, either fully disabled or fully active. Mid-range calibration actually degrades performance by oversmoothing diagnostic markers. When tested across 6 distinct brain and heart datasets, BioFormer outperformed 12 established baselines, pushing absolute F1 scores up by 6%. More importantly, it successfully decoupled subject-specific clustering from task-related patterns, proving robust in strict cross-subject evaluations. By reframing personal variability as a frequency domain alignment problem, BioFormer shows that better medical AI doesn't require heavier models. It requires smarter mathematical priors. And that's a massive step toward deploying reliable, generalizable diagnostic systems in the real world.